Yeah, Nate.
Hello, hi.
Hey, hey, nice meeting you. Yeah.
Yeah, I think I think we have new members like joining today. We can all introduce ourselves once again, and then we can start with the session.
Yeah, I can go first then. So my name is Sujit Paul. I live in California. I have been working with machine learning for quite a few years, like at least 5, 6 years now. Yeah, probably more. Most of my focus is on search and NLP. So that's how I got introduced to this whole, even machine learning, neural networks, what have you. Mathematically, mathematical sophistication wise, I can read papers, I can understand them, and I don't remember everything about linear algebra, so I've just been reading chapter 2, so there's a lot of stuff that I just I'm recollecting back. But usually I can work my way through papers, but that's about it. I tried reading this book once before, and then I gave up or stopped. So this is like I'm being forced to read, so I actually like this. That's why I'm here.
Awesome. So I think I can go ahead. I think I am Amit. I am currently residing in Gurgaon, near Delhi, in India, and I have been inclined towards computational geometry since 6 to 7 years. And right now I'm working on the intersections of NLP and computer vision. But it's primarily my personal interest to understand the intricacies of generative AI and the how can we intersect different areas in deep learning. So this is this is very interesting to me, and this is one of the reasons that I'm reading this book. The other reason for reading this book is that the author of this book, Ian Goodfellow, he discovered uh, generative adversarial
GANs, right? Yeah,
networks,
yeah.
GANs. So I really want to know how he and other authors think by learning about what they have told in the book.
Cool.
That is it. Does anyone want to introduce?
Yeah, I could go ahead next as long as I have a normal connection. So, hi everyone, I'm Lisa. I'm currently doing my PhD in computer science in Copenhagen, Denmark. So, and it's kind of stormy here today, so I might keep dropping on and off the call. Not sure how long my connection's gonna sustain. But yeah, I work with like large language models and I'm interested in the reasoning capabilities of these models. So I'm kind of working in the space of like compositional reasoning, generalization, mechanistic interpretability, all with LLMs mostly. And yeah, I think my main motivation for reading this book is because I've never had like a formal, proper course intro on the math behind ML and DL. So this book is probably going to give me like a good grounding, even though I read a lot of research papers and I know everything on the surface, but it's always good to have like strong basics. So yeah, that's my interest in reading the book today and look forward to learning with you all and from you all.
Awesome.
I can go next. Hi everyone. My name is Suman Devnath. I work with AWS with the developer advocacy team for machine learning. So I work as a principal developer advocate for machine learning. So I'm coming from a systems background. I worked in systems and storage for almost 10 years or so, and then I got into AWS. And at that time, I I had no idea about machine learning, and I started to, as part of my work, I had to present at various conferences, talking about technology like PyCon, data, uh, SNEA. There is a forum called SNEA for storage and all that. And that's how I came to know about machine learning in 2020. I was just blown away by one of the sessions at PyCon. And then I asked few of the other members that what it is. What, can you just explain me a bit more about that? So that motivated me, and I started to learn from few of the applied scientists, on YouTube, and few of the programs which are available online. And that's how I tried to move within Amazon to the data science team, and that's how I end up in this role. I find myself very fortunate that I got this opportunity without any formal education in this field. But now that I have the role, I wanted to get a more, I want to justify my role even more beyond what I am currently responsible to do. And that's how I started to go back to the basics and started foundational learning. I started with mathematics, and that gave me an motivation to study. So I'm study just for learning. There is no outcome that I'm expecting, but I feel very confident when I find how things actually works under the hood. That gives me a lot of confidence on something which I can do anyway. So that is my motivation. And during this last couple of years of exploration, talking to brilliant people in the company as well as outside, I wanted to pursue my next phase of my career towards teaching and research, and I think and I was lacking that forum where we have students, researchers, because they have a different mindset than who work in the company, because we are very much product centric, and there's a different notion that comes in. So I'm glad that I got to meet all of you, and looking forward to learn and as well as contribute wherever I can, and which might help me to take me to the next goal towards research and teaching in next 4 or 5 years from now. So thank you so much for giving this opportunity for all of us to come learn and and share knowledge.
I can
Awesome.
go
This is like
next.
very, very inspiring. Yeah, please, please.
Yeah, sorry. So I'm Manish. Currently I like stay somewhere between Bangalore and Pune. Like keep switching between the places. Currently I'm working as a senior data scientist in Bangalore. Uh, I have done my master's in computer science, so that was kind of my first introduction to machine learning. Majority of my focus has been in forecasting for like last 3 4 years now. Uh, I've been planning to read this book for a long time, but never had a formal structure where you can actually follow through. You read one chapter and then maybe you don't read anything for next month and you just forget everything. So that's why I came across this group like a couple of days back, and hopefully, yeah, I'm hoping that it will help me to stick to the book and finish it. My main goal from this would be I've used some sort of deep learning and forecasting in LSTM and all. I've used TensorFlow and all those things, but I never got a chance to actually understand the math behind the deep learning. So with this book, I would like to get a good theoretical understanding background in deep learning.
I think I'll go next. Hi, everyone. I'm Sagari. I used to be a data scientist at Philips. I used to work on deep learning and medical image analysis problems. Right now, I've recently moved to the United States. I stay in Indianapolis, and I'm looking out for new opportunities over here. The reason I've joined this study group is actually I've never read a book on deep learning. It's mostly papers and maybe after that it's just reading a few blogs and stuff like that. So I've never gone through a book chapter by chapter for this. And also, it's been quite a long time since I've gone through the mathematics and the theoretical basics of deep learning. It's once you get into actually practically using in an industry, you tend to forget some of your theoretical basics. So you want to dive deeper into some of those aspects. So my motivation for joining this group is just to be a part of the community and just trying to get through it together and also be introduced to people around you. So it's nice to be here. Thank you.
Great, great. So I think like I'll be presenting. We'll go ahead with the introduction chapter. Like, have you all read it? The introduction chapter of the book. I
Intro,
mean,
yes.
just about the organization of the book and what is deep learning and the history. I'll just briefly go through it. And I think we have Ruchira today presenting the second chapter, but she has poor connection due to a storm in Denmark, I guess, this time. But let's see if she can join again. So I'll start presenting. Can you guys see my screen?
Yes.
Okay. Yeah. So I've created a very short PPT. So the first chapter is about three parts. It is about what is deep learning in general, and what is AI, what is machine learning. And the second part is about, so I've switched the order of the parts. Second part is about the history of AI. So again, there are three parts in that. And the third will be of the organization of the chapters of this book. Okay. So can anyone think of a challenging task for machines back in the day? I mean, people created calculators long back, and then they started to think that they can perhaps create machines which can think about some problems that human are not able to solve, or they're harder to solve. But while dealing with and while creating such machines, they had to face problems. So, like, can you think of a task that is easy for us humans to perform, but it is harder to describe? Like what we have done, like how we have solved that problem. We can
Yeah,
solve the problem, but it's harder to describe.
I remember reading in the book where the book talks about intuitive tasks that are easy for us to do, but hard for us to code it in terms of rules about the world. Everything about the world in terms of rules for the machines, and machines are good at the logical rule-based task, but that is complex for humans. So I think that's what the book was talking about in terms of the challenging tasks, I guess.
Yeah,
Also,
sure, yes,
also,
please.
also object recognition, right? I mean, for a person, you show him something, right? You say, okay, here is like an apple, right? And that's the only training example you need, right? So you now know what an apple is. With a machine, you don't, right? So, or you can actually generalize at
Yes.
that point and say, okay, I've seen an apple, now I'm looking at a pear, I'm looking at some other fruit, and they're all fruits because they look like an apple, right? So soft
Yeah.
prediction.
Yes. I think one more example could be similar to the recent example, is that facial recognition, right? And we identify faces very quickly. For example, you all know who this is, right?
Mm-hmm.
So can anyone tell me
Who this is? He's a movie star.
Yeah.
I forget his name though. Sorry.
Yeah, he's a movie star. His name is Tom Cruise.
Yeah, there you go. Okay.
Now it's very easy to identify whenever we look at his face. It's very much clear to us and we remember his name. So we are able to identify very easily, which was, if our task is to identify people by looking at their faces, it's easy for us. But how are we able to perform it? How did we come to that conclusion mathematically? It's very hard to describe to other people. So at present, what the book is telling us is that right now we are dealing with such problems that are easy to perform, but their solution is hard to describe among us. So facial recognition even we can do, but for machines to do it, we have to give them some logic, which is hard for us. Can you give an example of a task that is easy to perform and easy to describe also?
Code.
Sorry?
Code, like add two numbers, right? So
Yeah, absolutely, yes. So, like, if you take like two simple numbers, and if you try to add or multiply, it is easy to perform and easy to describe methodically how to do it. But if you take long numbers, they would take some time to perform. But again, it's easy to describe what we have done, and that is what made it easier in the earlier days to create calculators, etc. Now, can you think of a task that is hard to perform and hard to describe?
for who?
For us, for humans,
Okay.
it is hard to perform as well as hard to describe. Even if we perform that action, it's harder to describe the solution. How did we perform?
Trying to figure out how much we learned from this chapter.
Okay. Yeah, I guess, yes. I think one of the examples that were given in the book, even that may apply here. That was AI defeating Gary Kasparov in 1997. So in chess. So for humans, it is very, very hard in general to defeat world champions. Like if I want to defeat a world champion in chess, it's kind of impossible right now. And so even if I defeat by chance, I think that would also be harder to describe. How did I defeat? So I think that problem is also one of the problems that we are dealing with today. One more example of this category would also be driving. Like driving comes through practical experience, but designing a self-supervised car, again, it's hard to perform, hard to describe kind of category, perhaps. So yeah, I mean, the first part of what is deep learning talks a bit about this. And then we come to know that deep learning is basically hierarchy of concepts. So there are complex concepts built out of simpler concepts. For example, this example is given in the book where we have pixels in the input, and in the first layer of the AI model, it identifies a pattern which are edges in the image, and then in the second layer it identifies corners or contours, and in the third layer some more sophisticated parts like eyes, etc. And finally it identifies whether it is a person, cat, or animal. So as you can see, deep learning is a method, is an AI technique where machine learns complex concepts from simpler ones through layered hierarchies. And in this example, okay, so in this example, we have not seen representations. But representations would mean like identifying what data would represent the input data in a much more better way. So can you give a simple example of representation? What would be a representation? Can anyone think of
Well, I mean,
how?
you could represent a fruit by its color, the skin color and the taste and the shape, right? So these three could be features. So the representation of the fruit could be these three as a vector of three things.
Yeah. So we have a fruit. So instead of taking the image, we can note its color, the smell,
Right, smell, yeah, sure.
or shape, or size, etc. I guess. So we won't require the fruit itself, but these 5 or more factors would just represent the fruit. So this type of data will be called as representations. And so here we have these diagrams where there is rule-based knowledge system where everything is designed and certain. Then it comes under AI, but not under machine learning, right? For example, can you give an example of something that is in AI but not in machine learning?
According to the Venn diagram, no, right?
Yeah, I can zoom it. Something that is in AI but not in machine learning.
Oh, I see. Okay. Oh, good. Okay. Maybe knowledge graphs.
Knowledge graphs.
Yes. So
Okay.
these are like
No.
human designed representations of knowledge, right? And it could be AI. You could have reasoning systems built on top of that, but it doesn't actually
Yeah.
use machine learning.
Yeah. Yes. Okay. Any other? Can Can a calculator fit here? Will it be a knowledge base where we are providing it with a multiplication algorithm, addition
Right,
algorithm?
yeah. I guess you could, yeah. It does.
So, okay. So I'll just write here calculator. Now, when it comes to machine learning, what is different is that in the right-hand side, you can see that when there was input in rule-based systems like calculator, we defined its entire logic. But in machine learning, what we are doing is we are first taking some the good data, which we'll call features, out of the input, and this is where that learning is going to happen. And this can change according to the training and testing. So it is a bit probabilistic and not that certain like calculator. So as you can see, one example of machine learning is logistic regression. And I think the example there of logistic regression given in the book was cesarean delivery.
Mm-hmm.
Whether to do a cesarean delivery in a pregnant woman. So it was used it back then, and they used logistic regression for that. So that is again an example of machine learning. But representation learning, the difference is that we are also finding out what the features could be the best possible features. And then we are going to map the function. Then we are going to find the function. So it will be a probabilistic method even for finding the features as well. Now, the difference between representation, learning and deep learning is that deep learning is just a model in which there are more layers of learning. So once we have achieved this representation, then there would be more complex, we can say, representation. And from this complex representation, then we find this mapping again. So due to this depth, we call this deep learning.
One other way I think, it's easy to think, at least for me, is that, when for regular non-deep learning systems, right, you use the human intuition, right, the person who is designing the system or his subject matter experts. So they use human intuition to come up with features that would be then fed into the, the learning system, logistic regression, Bayesian network, whatever. Whereas with deep learning, you basically throw compute at it, right? You say, okay, you have a lot of data, so you throw data and compute, sorry. And you basically say that, here's the data, here's the label. Now use compute and use all these massive layers of, deep learning, these feature interactions, right? To basically come up with the best weights for those features, right? So a lot of those features might be junk features, but because, you're computing, at the end of the training, you will find that those features will have very low weights, right? But you have not designed it. You have not designed the features. You have basically given him the data and you have given him the compute and it figures out the features. So I think of that as a easier way to think of deep learning, just sharing.
Yes. Yeah, I mean, like the main thing would be not designing the features. Yes, in deep learning. Great. So Yeah, I think we can proceed
Yes.
further. So I think I've taken the second part as the history. So does anyone have any question, or does anyone want to discuss anything up to this part? Like, what is deep learning?
Yeah, one small.
Sorry, go ahead. Yeah.
Okay. Yeah. So
Okay.
when we discussed about a calculator, isn't it very much rule oriented? So does it actually comes under AI, or we can have it outside? This is a rule based system where we know if the function takes X, what should be the output Y?
Okay. I mean, even I'm confused a bit, but I think that since we are providing with an algorithm to work in situations which are certain, although there's no probability involved, there's no randomness, I think still we are providing the machine with some information or logic.
Mm-hmm.
So I'm not sure if what is not in AI.
Yeah.
Well, I mean, you could think of it as a diluted version of the Turing test, right? So a calculator is, you're giving him things to a couple of numbers, and it's giving you like products and whatever, right? So if you put it in behind the wall and you just said, here is two numbers, add them and give me a result, it does it, right? So that intelligence, in quotes, right, is indistinguishable from a human. If you did not know it was done by a machine,
Yeah.
right? So in that sense, I think you could call it intelligence, right? One other example I was thinking of while you're talking, right, is prompt engineering, right? So we are using these LLMs which have been trained on massive amounts of data and so forth, but in reality, we are really telling the machine what to do, right? You say, okay, here is a prompt, and here is what I want you to do with it, right? So, and then it does something, and so you're essentially using it like a glorified formatter at that point, right? So so prompt engineering in that sense. So when you're not doing, say, few-shot learning or any machine learning kind of things, I think even that could go into AI and not ML.
Mm-hmm. Yeah.
Right.
Interesting. I have a question regarding prompt engineering. Like, what if, like, I mean, can we get a different output for the same prompt if we give it again? Like, I think
Yes, you can. Yes, you can.
So, I mean, is there a differentiating factor for that? Like, if we have constant input and multiple outputs.
Okay, so rule-based versus that's a good point, I think. Yeah.
Yeah, it's a bit. I mean, definition-wise, I guess I'm not sure how we would like to classify whether a machine is intelligent or not.
Right. Yeah.
But yeah, I mean, very interesting prompt engineering. Yes. So okay, so let's go ahead, I guess. Uh, so history of AI, three parts of the history are discussed: cybernetics, connectionism, and deep learning. So I think I've not uploaded yet, but let me just. Yeah. So in cybernetics, we had uh, linear models. So cybernetics, I think, came in 1940s to 1960s, and it was, I think, it arose due to thinking towards how brain functions, I guess. And so what researchers did that time, they developed linear algorithms for solving problems with weights. And there was this famous Nacular-Spitz neuron, okay, which was an early model of the brain function. And although they tried to improve that model, they found out that it failed for the XOR function later on. And also in this period, they also discovered stochastic gradient descent. Yeah, I guess. But this model, this phase, and these models failed because they were inspired by biology, okay, in general. And then they found it out that uh, neuroscience is important inspiration for deep learning, but it's no longer the predominant guide. And it is also said here that we do not have enough information about the brain, I mean, which makes sense. So it's very hard to rely on just thinking how brain functions and try to decode it mathematically. Then the rectified linear unit was also developed, but the dates here are a bit different. And okay, I think we can skip that, but no.
Yeah, all these names are, current, right? Hinton,
Yeah,
Lecon.
yeah. So I'm just trying to figure out the most important points out of this. Like this is like so much theory. I'm never comfortable with theory in general, but
Yeah, I think that's all there was during the cybernetics phase. Basically,
yeah,
they were inspired by brain and they tried to create artificial neural networks, but they couldn't fully accomplish certain tasks, and they were facing a lot of failures. And because they were taking brain as inspiration, they couldn't actually model it completely, and they stopped at that point. And out of that, as you mentioned, out of that phase, the important models or that we got was the linear units and gradient descent. These were the two things
yeah,
need to be remembered from that phase. That,
yeah. Yes,
yeah,
yes, yes.
that's like a summary.
Yeah. Thanks, Sagari. I
No
think
problem.
we can just write here. So this is mostly linear units, and gradient descent And I think linear units failed on XOR. Okay. Now coming to connectionism, where again they tried to connect it to the brain. Uh, Here also, I think it was they tried to, the central idea in connection is that large number of simple computational units can achieve intelligent behavior and network together. So they tried to distribute the tasks and basically do multiple tasks at a single time. Then distributed representation. Yeah, each feature should be involved in the representation of many inputs. Okay.
So instead of one ANN, they basically hooked up a bunch of ANNs together, right? And created like hierarchies of like a modern neural network. But is it still linear? If it's still linear, then it will not work, right? They probably used
Yeah.
nonlinearities at that point.
Yeah, they did use nonlinearity.
Yeah.
Yeah, I think nonlinearity was introduced, and I think back propagation was also introduced in this phase. Okay. So why did this phase did not achieve?
Hardware, I think. They didn't have the hardware speeds.
Okay. Yeah, I think one of the reasons was hardware, and there was one other reason.
So at the time, simple models were performing as good as the connected neural networks.
Okay.
So that was another reason.
Okay. Yeah.
At this time, they also
So,
introduced
so
LSTMs for sequential modeling.
Oh, during
yeah,
this period. That's interesting. Okay.
Yeah.
I think they have mentioned it, yes, here on. But this was in 1997 or something, right?
Yeah, Schmidt-Huber. Ockreiter and Schmidt-Huber.
Got it. So,
It's probably between the two,
okay.
right? I mean, yeah.
I think my dates are wrong probably here, but I think it should be 1980s to early 1990s, something like that. 20
Yeah,
years
there was a,
or
what was
something like
that,
that.
deep learning winter or something, right? So 60s to 80s, like 20 years, there was nothing. So yeah, you're right. I think it was 80s.
Yeah, 80 to 95.
Yeah.
The figure had the periods for each phase.
So we have LSTM here. Then in connectionism, we have distributed the computation. Distributed computation. Then I think we have yeah, again they were trying to imitate brain. So
It's more like they were trying to be inspired by the mind, like how connected everything is, and the mind can do uh, different tasks at the same time. So that's why connectionism, the name came from that. So they try to connect the different computational units together to achieve intelligence.
Okay, so the distributed and part is like the major
Huh.
part.
Right.
Got
Right. The
it.
distributed representation is the major thing.
Okay. Then coming to the third part, which is discussed, that is deep learning, which first began by the results of deep belief network in 2006, where they used greedy layer-wise pre-training. Has anyone gone through what is this greedy layer-wise pre-training?
This
Any
is
idea?
like, yeah, I can probably say this. So there was something called Boltzmann machines, right? So because they didn't have enough compute power, what they would do is instead of training the neural network end to end, they would train each layer, right? And then use the pre-trained layer, and and keep going forward with that. So that's yeah. There is it's actually I think it's called Boltzmann restricted Boltzmann machine, RBF, RBMs or something it's called.
Okay. Great. And so it basically outperformed all the algorithms that were going on, and then rose the area or era of deep learning. Great. So, okay, coming to data sets discussed, I think over the time we see that uh, they have reached billions. Some of them Canadian Hansard, then 2015, near to 2015, all have gone up. ImageNet 10K, WMT. And this is a very famous data set of handwritten digits in history. Then increasing model sizes, number of connections per neuron, that also increased over time. So, like people were thinking about this architecture since long time, but it was the computational and hardware uh, which was lacking, like what I felt. Hmm. Hmm. Any
Yeah.
interesting insight over this graph?
If you
This is
look at
like
the
going like,
previous one, so
okay.
I mean, I don't know if you follow Jan LeCun on Twitter, any of you, but he keeps making the point that the way we are doing neural networks is not going to lead us to true AGI because current neural networks have the neural capacity of a cat, right? So, and I just noticed this here. If the figure 110, right? You see the cat line
Yeah.
here? That's,
Yeah.
close to where. So I just saw that and, I realized that, that's what he's talking about.
Hmm.
Yeah, that's like the number of connections that we have in our brain.
In fact, he also talks about like the current architecture might not lead us to
Right.
that
Yeah.
revolution.
Yeah. But the point he makes is that, the current neural networks have the neural capacity of a cat. And I didn't know where that cat came from. So now I know.
So it's good to go
So,
back to the history to make
Right.
sense of this.
so is it like that even if we have good architectures, the designs in future, we won't be able to cover the computational hardware that is required, which a human being has? Like, do you think that
Well,
we can achieve
yeah.
the hardware where it is capable as thinking as like humans?
I mean, definitely it's a different way in which we are going, right? I mean, if you think about our brain, what is the electricity requirements for that, right? Power requirements for a brain compared to, okay, LLMs are kind of approaching, brain function, maybe, even though maybe not, right? So it depends on which camp you're in. But you look at their power consumption and you look at the brain's power consumption. I mean, we are obviously doing something different. I'm not saying right or wrong, but, different, right? So
Yes, yes. Okay. So yeah, so these are
Sorry,
the
one
list of labs.
question.
Okay.
Can you
Yeah.
can you go back to that graph, first one? That
This one?
yeah. So does it say that the difference between human connections per neuron and cat is only that much? Like
it's a
10 to
log
the
scale, though. Yeah.
I think
oh,
they have not given this on scale, the human part, probably. Like this part.
no, because the last line of your figure, right? Even that says even the human brain does not have an exorbitant amount of connections per neuron. Does not have.
Yeah.
Like
Yeah. Yeah. There is some finite limit, yes, I guess.
Yeah, so it's I just pasted one image in the Slack. You can check it later on. I'll share the link as well. So I think what Sujit also mentioned, right? So it's kind of an intuition that how we started off with, let's say, like with the synapses and then transformer, mouse, cat, and today, although we have models with trillions of parameter, and we feel that it's kind of doing magical work. But still, when we compare with the humans' level of understanding, we are still way far away from there. So, and it's in the exponential scale. So it's like a cat has, let's say, 10 to the power 13. Human is like 10 to the power 15 is what I read in that lecture. I'll share the link later on, but that lecture is from IIT Madras deep learning course from Professor Mitesh, and their slides are very nice. Like it has been created based on this book because this is the reference book which they used. But a lot of the things that Amit and Sujit mentioned are actually, I learned the same thing from there. Yeah, you can check. I'll post that link maybe on the Slack.
Cool.
cool. Thank you.
Actually, I did not see the logarithmic scale. Now only I saw. Yeah, like as we go ahead, this small difference will also be large.
Right.
And okay. Uh, okay. So we have all these architectures, which so this is again a graph depicting neural network size, number of neurons, logarithmic scale again. And you can see human is just way ahead here also. Okay, let's dive. I mean, I think we can. Do you guys want to discuss anything else? I can skip the rest of the history now. Go with the organization of the book.
Sure.
Yeah, I think. Oh, okay. I also wrote. Okay. There is. So the book does not discuss history after 2015. So just to bring it out there, I wrote the 6 areas in deep learning, and there are more actually. Correct me if I'm wrong. And so, for example, computer vision. Can anyone think of human analogy of what computer vision would depict, and what are we trying to imitate if we are trying to imitate in computer vision? Like, for example, I can just say that for computer vision, perhaps I can say that. So it's, I think, eye and brain coordination.
Are you talking about the neural link, Elon Musk's implant, or something else?
No. I'm talking like how we function, right? Our eyes and our brain are connected in some way that whatever.
I see. Okay. I see where you're going. Okay. So yeah.
For computer vision probably it is eye brain coordination. What can you think of reinforcement learning?
Almost all teaching is reinforcement learning, right? I mean, you teach a kid how to do something, and then you punish him or you reward him. So that's
I guess a bit hit and trial,
right.
etc. and learning. What about natural language processing?
Learning to read. I mean, how do you learn to read?
I mean, to understand languages better, I guess.
Right. Yeah.
Yes. What about generative AI?
We do that, right? I mean, once you learn to read or you learn to see, well, I mean, those are obviously the kind of inbuilt. You could paint, right? People who do art, for instance, even people who do literature or people who code, right? They're all generating stuff, right? So in that sense,
Yeah. Yes. We can perhaps say imagine or create something new.
yeah.
What would graph machine learning look like in human analogy? Like what are our tasks that would represent graph machine learning?
Making
Can anyone?
connections. So based on
Yeah.
our knowledge, so you could think of the knowledge in our heads, right? The things that we pick up as some kind of graph mechanism, and then we make connections between them, right? So for example, let's say you're looking for a job, right? So you would know that you would try to make the connection between the JD and your skills and see if that's appropriate for you to even
Yeah.
try.
Yes. So making connections and relations in different topics.
Right.
And what about speech and audio processing? For example, I'm talking about speech detection, like understanding what is in that speech and perhaps creating new speech.
Yeah, both of which we do.
So
Yeah, one interesting point. This is also from Lekun. So he makes a point that, for computerized speech processing, you need to know both the grammar and the language, right? So you need to know the vocabulary as well as the grammar, right? So, and because if you want to segment the the incoming sentence, right, into pieces that can be then parsed separately, you need to know the grammar, and you need to be able to tell what the tokens are, right? Where the tokens break. So you need to know the language, right? So the vocabulary. So yeah, probably unrelated, but it's kind of think when you say learn to speak, right? So you need to know two things there.
I think, and here also, I'm like,
Yeah.
okay,
Yeah.
great. So I have just written down some of the architectures, I guess. So these are like some of the architectures in these fields from 2015, 2024. You can just take a look at them. And if you want to like suggest a missing architecture, please do that. So In computer vision, we have YOLO, ResNet, UNet, Mask, region-based CNN, PointNet, etc. And I think this is launched by Meta in 2023.
Sam.
SAM is also there, I guess.
Right. Well, that's the segmented thing, something, it's that's Sam.
Yeah, segmented models. Yes, yes.
Right. Yeah.
Yes, yes. Sorry. Then over the years, we have seen AlphaGo defeating world champions, AlphaZero, AlphaStar in reinforcement learning. We have R2D2.
There is clip
So
and blip. I mean, if you want to, well, you have put VIT there, so it's probably clip is covered.
yeah, I think Clip is in 2022, perhaps. I'm not sure. I just was looking for architectures,
Right.
the major
Yeah.
architectures.
Right.
Yes. And okay, we also have stable diffusion, which is also stable diffusion, GAT, CRISPR, GNN, GCN. Then I think in this book we won't be covering GAN, but I think it will lead to that, perhaps. Great. So so if we just want to make a timeline, I mean, of the information, right? So we saw that 2015 to 2024, then from 1940s. So this is not up to scale. 1940s. So, and this is, I think, 1600s, etc. So I think 1600s was the time when calculus was developed.
Okay.
And then we have linear algebra, etc. later on. And probability is perhaps like way back, but still after linear algebra, then the concepts enhanced. So the very first few topics that we'll be learning in this book will begin from like will be of this era. I think this is the part 1 of our book, and this will also be like ML basics here. Then I think machine learning basics that we'll be covering were also, I think, discovered in 1800s. So the part 1 of this book will be dealing with the information that was created way long back, around 300 to 400 years back. Then we'll be dealing with part 2, that is deep learning foundations. Then that would be, I think, the architectures would cover this part. Yeah. I would say this part. This is part 2 of the book over the timeline. And part 3 would perhaps be like very close to. So you read after this, we would have to do something else. Okay, so yeah, as I said, 3 parts are there in the book. First is mathematical foundations, machine learning basics. Second is the foundations of deep learning, common architectures. And the third is deep learning research, including deep generative models. and this is the graph, dependency graph. Anyone wants to discuss the chapters of this book, like, and are you guys interested in reading all the chapters, or do you want to read only some of the chapters? So, like for me, I am interested in reading all the chapters, but I can still understand if you're not interested to read all the chapters.
I'm looking at them. It looks like they might be interesting. Even the part 3 thing, right? So there is, it's, things like I would like to learn more about. Chapter 16 and 17 definitely, right? So structured probabilistic models and Monte Carlo methods.
Okay.
Yeah. And deep generative models, I'm guessing it is talks about GANs because it's his book, right? So he might have some initial thoughts about GANs here.
Yeah, I think, yes, definitely the initial thoughts. But I searched for the term GAN, I mean, generative adversarial networks. I did not find it, but I'm not sure. I think still this will cover the intuition of GAN, probably.
Right. And one thing I noticed, right? So, like if you are doing applied stuff, right? Usually, and even if you're doing academic research, I think a lot of papers you'll find is that they look at the current techniques that are available today, and then they apply some old concept to those techniques, right? So in Gen AI, for instance, they're going back and picking on things that so maybe like extracting entities, right, and using it for graph lookups, and then they're looking for paths in the graph, and then adding it back to the prompt. So there's a lot of stuff that people are going back to the old methods, pulling it out and applying it to their new techniques, right? And they're writing papers on it. And I think that is also true for applied stuff. One problem that I had recently was I went back and did logistic regression because I didn't have enough data, right? So and logistic regression actually worked, right? So yeah. So it's good to know these things, I think, even though,
Yes. I think in the machine learning basics that we would have, the 5th chapter, it's probably, I'm not sure if it covers everything of machine learning. And if someone really wants to read machine learning, then there are other books like Elements of Statistical Learning, etc. Great. So yeah, I think that's it. We have covered the entire chapter. Now we'll take a 5 minutes break. I'll just see whether Ruchira is joining. Has she joined? So we'll take a 5 minutes break. We'll be back, and I think I can go through the linear algebra chapter for now. Let's see how much we can cover. If you guys have anything to discuss, please let me know during this break.
this is with reference to what Manish said during his introduction, right? Talks about equations, right? So this is like an experience I had basically. So during the time LSTMs were popular, LSTM grew and all these things. So I had a hard time understanding how they all work because I was looking at the diagrams. And then I went and looked at the equations, right? And at that time, like people were doing spin-offs on LSTMs, right? They take the basic architecture and then they change something and they get some results and they write a paper on top of it. So, and all the time, every time you look at a paper, they would publish the updated equation, right? it's a LSTM has just 4 equations. GRU has, I think, 3, right? So, and if you know those equations, you can actually, you don't even have to read those additional papers, right? They will publish their equation, and you know instantly what the difference is, right? And you know how the paper is achieving what it is doing, right? So I think understanding the equations also is quite useful.
Okay.
Yeah, I agree.
Yeah, also sometimes in the papers, each paper, sometimes the notations might be different, and
Yes.
you'd think, okay, what is this new equation that they've introduced? But then when you know these basics already, you just be able to understand the differences. Oh, they've just added a new notation that
Right.
is different to what you already know. So it makes it simpler when you know your basic equations and you build up on that when you're reading papers.
Yeah.
Connected with your classical machine learning, once you know your MLE, MAP, and maybe generalized linear models, most of the things make sense for you in the classical machine
Yep.
learning.
Yep.
But if you don't know that, then you're just trying to figure out from where the hell this equation is coming from.
Right.
I actually have a question. I wanted to know what neural Turing machines were. They were mentioned in the book, but I actually didn't understand. They just like mentioned a line about it. So, does anyone have experience with it or understand it?
Neural Turing machines. No, I can. Does anyone know?
I don't.
I just asked ChatGPT. Designed to combine generalization capabilities of neural networks with algorithmic power of Turing machines.
Okay.
Yeah, there seems to be 2014 Graves. Okay, so that's. It could be something like the recent you know how what's his name? Those the MATLAB guys, right? So right, so they had a blog post recently where they said like, LLMs are not good at doing math or doing like actual computational work, right? Guaranteeing that it's correct. They are good at spinning, like basically generating text, right? So why not, hook up an LLM? So whenever it sees a math question, it basically delegates off to MATLAB. So again, agents, functions, what have you, right? So, and then you get back the response from, it's not MATLAB, it's something, maybe it's MATLAB, I don't remember. So, and then you get back the thing as context and let the LLM return the response.
Oh, so it's just acting like a messenger between two,
Right.
like an agent between two.
Right. Well, I mean, at least that is what I understand from, what I read about neural Turing machines. Maybe it's not exactly that. But,
okay. Yeah. I just wanted to know if anyone had any experience with it. That's all. I mean, I'll read about it online. That's fine. Thank you.
Sure. And maybe post on the Slack, I mean, what you learned, right? That way everybody.
Sure. I'll let you guys know.
Shall we start?
Yeah.
Am I audible?
Yeah.
Yeah. So today let's do one thing. Let's cover the basics of linear algebra and let's solve some problems. If we get time, we can do the problems on SVD and PC as well. Okay, so linear algebra is, again, it's mathematics about, I would say, linear systems in nature, in your observations of nature, and the history. What I think is it's very easy for us to predict anything in lines or in linear proportion. So I think this would have been one of the most fundamental topics in the history, because it was probably easier to think of it. Talking about scalars, any single number with just a magnitude and no direction or is a scalar. And then vectors are represented like this, where there is always a single column and multiple rows, and number of rows is equal to the dimension of the vector. Then matrices, the terminology used here is only for 2D array of numbers. So something like 2, 1, 3, 0 is a matrix. You can perhaps interpret it as two vectors like this. I don't want to go into this notation, but like this is one vector, this is one vector. So it's kind of like bag of vectors. A matrix is a bag of vectors. Then tensors is in general n-dimensional matrix, where so in every dimension you have different number of vectors, right? Then transpose. So can anyone, so those like very basic questions. What would be the transpose of this? Just reflect it over this diagonal. You will get 2 as it is, 4 as it is, 1 year, 0 year. Now, if the matrix is not square as it is shown here, you can take that reflection across this very first, this square, top square. And if it is looking like this, it will become like this. So transpose is done. Addition is just adding individual elements, corresponding individual elements. So to add corresponding individual elements, it must be necessary, is necessary that both the matrices have same shape. If you want to add a matrix and a vector, then it is the vector is added to each row of the matrix. So if A equals to 3, 2, 4, 1, and if B equals to -1, 2, can anyone tell me what will be A plus B?
Oh, okay. So 2 and then 3, 2, 3, and 0, -1.
Yes, I guess. Yes. So
Might be worth knowing the broadcasting rules as well. So I use this a lot when I pasted the link to the NumPy broadcasting rules. So it's quite comprehensive. So.
yes.
So Sujit, do you remember it or do you just use it as a reference? Because there are so many
I use
rules.
it as a reference, and the only times I actually refer back to it is when I'm getting wrong results.
Yeah, that's true. That's when we usually need it.
Yeah.
Otherwise,
So,
we just go by intuition. We just try to
yeah,
make it
yeah,
work.
yeah.
Thank you.
So like in this case, would this A plus B would be 2, 6, and 1, 3?
2, 6, 2. Why 6?
No.
And they have defined like B is added to each row.
Yeah, so I think if you see here, when we say this is my intuition and understanding, if you look here, we say vector B. So the vector, when we say any vector, we can write it. No one is stopping us to write that vector as a column vector or a row vector.
Yes.
Completely up to us, right? So, but the assumption that I've seen in most of the books and research papers is if there is no mention or a row, whether the vector is a row or column, it's safe to assume that we are referring it as a column vector. So, and that's how you have also written b as -1. Now, when we add this, we just add that column vector with each column of A, which in another way,
Okay.
it's same as adding each row of the matrix. So the way that I look at any operation in matrix is always through column, but it's a personal preference. But here, if you see the matrix A have 2 columns, and when I get one more vector like B, I will just add that vector to each of these columns. But one other thing that always confused me is when there is no mention whether that vector is a column vector or row vector, and that's how this broadcasting and all this thing come. I personally feel broadcasting has nothing to do with linear algebra as such. It's more on how, when we compute that in a computer, what makes
Yes.
more sense to us, and that's how it comes. But because broadcasting has nothing to do with vector space or anything like that. There is no, we cannot do any operation which mathematically doesn't make sense. But when it have to do that in a computer,
Yes.
we have to somehow make things up.
Yes, yes, definitely. And I mean, like, just for the sake of the book, I mean, like, because if there is a notation ahead representing the addition of matrix and vector, I think we can just follow the definition given in the book. I'm not like, does this say that it is adding the vector for each row? I mean, am I doing it correct? Because it's more logical to add column wise. Yes, and it's intuitive also, but they're
Oh,
saying that.
yes. So here they are saying correct. So they are saying that add the vector B to each row of the matrix. So you have written B as a column vector, and then you have to add it to each row. But yeah, I'm also a little confused, because if you see here, the vector B, it says Bj. That means that is kind of same size, the dimension of that, like J and Aij. So that is, it's a column vector.
Column vector, yeah.
Yeah.
And now when
Yeah.
we say, right, yeah.
Yeah, actually they defined it, the vector also, they have defined it like that, like column vector here. I mean, probably that is
In
a
general, we usually, if it is a vector, we usually consider it as a column vector. Very rarely.
column vector.
Yeah, unless otherwise specified, if it's a vector, we usually take it as column vector itself.
Yes. So I think in this book, we can follow this notation of A plus B, where we are adding it row wise. Okay, then matrix multiplication again is fine. So I just saw this on the video of Tree Blue and Brown on YouTube, and they just showed that multiplying two matrices, uh, if there is a multiplication even with a vector, let us say 2 cross 2, 2 cross 1, and some numbers here, 3, 5, is nothing but 3 times the first vector in the matrix plus 5 times the second vector in the matrix. Okay, so we can visualize it like that also. Matrix multiplication can just break them down into vectors.
Is it commutative though?
No, it's not commutative. It's not commutative, but it's associative with multiplication and addition. So Only it is commutative for between two vectors, dot product between two vectors. Because the result is scalar, I mean, just 1 cross 1.
Right.
Then transpose, this is the definition of transpose. I won't say definition. I think this is equal to the transpose. You can get this by following the rules. Then again, product of a scalar value again like this. Is equals to this, because again this is 1 cross 1. So even the transpose is the same of dot product. Okay, then solving linear equations. We can represent linear equations in form of matrix Ax equals to b. And there are many ways to solve such equations actually. It is not mentioned here, but I think Gaussian elimination and other stuff, which is in general, are you guys aware of the techniques to solve these equations?
Yeah, I think in terms of simultaneous equations, in school, right, they taught us. So some of the insights that are here, where it says like, the number of equations should be greater than or equal to the number of variables n, right? And that's true because otherwise you cannot find a solution in case of simultaneous equations, right? Also, the other thing that they talk about is if you have like two equations which are just multiplicatively. So if you say x plus, so you say x plus y equals say some number 10, right? And then you say 2x plus 2y equals 20. Those are meaningless. They don't actually, the second one doesn't give you any additional information. So you will not be able to solve the equations, right? So I think a lot of the insights, I'm kind of putting it back in what I learned in simultaneous equations in school, and those kind of work it is.
Yes. I think, I mean, we are talking about dependent, independent
Right.
vectors, system of vectors. And I think for this equation, what we can just do here is Ax equals to b. You can just take inverse both sides, right? So to define the inverse, I think they have defined it here. And identity is again with respect to multiplication. What would be identity with respect to addition? Can anyone tell?
Zeros.
Yeah, all zeros. So the inverse is defined that for all x, I think this is the definition, or you can just say that if Ax equals to A.
Yeah. It's a
So
diagonal of ones, basically, right?
This identity. If Ax equals to I, then x is A inverse, and if even xa will be equal to I in that case.
Yeah.
So whenever inverse exists, we can just find that inverse, and that will be our solution of, I mean, that will give our solution here. Inverse.
Can you just scroll up? Can you just repeat this part? Ax equal to I?
If Ax is equals to I, then we can probably say that x is inverse of A.
Yeah, so here x is an vector, right?
Yeah, I mean, like, yeah, I should have taken some other notation. Just thank you for correction. Yeah, I think we can take the capital X perhaps, which represents a matrix.
Yeah.
Then we can say that X is a matrix which represents the inverse of it. This we can use it to solve this equation Ax equals to B. And when A inverse exists, there are several different algorithms to find this A inverse and solve the equation. But here they have said that A inverse is useful theoretical tool, however, should not actually be used in practice for software applications because A inverse can, okay, there is only limited precision on digital computer. So algorithms that make use of value of B, that make use value of B directly to compute X are more efficient and accurate instead of just computing A inverse.
Actually, this part I think I was confused. So could you explain this part? What are they trying to say?
They are saying that even if A inverse exists,
Mm-hmm.
Computation of A inverse directly can cause computational errors
Okay,
due to limited precision.
right.
So instead of that, there are some techniques where to solve this equation, we just modify this and we just change this somehow to I identity and we modify this to get the answer. So that the process of modification is perhaps not giving errors in computation.
Uh, how are we modifying it?
There are some techniques like I think one is Gaussian elimination, if I'm not wrong.
Okay.
Gaussian elimination.
So are they saying if you're using it practically on a computer, you're modifying it such that it doesn't give you any computational errors, and then you'll be able to get your B accurately? Is that what they're trying to say?
Yeah, it's more accurate, I would say. I mean, I think there might be some errors also here also, but I think it might be more accurate.
Yeah,
Mm-hmm.
in fact, I also thought about this, why they said that. So one of the things that I was just thinking around is imagine that because we are computing about we are talking about A inverse. So if you think about it in mathematically, if I just do it on a pen and paper, A inverse, I have to take the determinant of that to find the
Right.
A inverse. So imagine that A is our data set of, let's say, 1 million rows, 1 million data points, and let's say 10,000 features. So now to calculate the determinant of a matrix of this many number of rows and this many number of columns, we take a determinant, and then you have to take the inverse of that. Like if you put
You
the
divide by the
yeah,
determinant.
so and it's all when we have a matrix of m by n and we try to calculate the determinant, we have to multiply the determinant of many subdeterminants within that,
Correct, correct.
and
Right.
one error will amplify. So computationally, we will see a bigger impact there. This doesn't hold good. I mean, this holds good for smaller metrics, but when it goes in a real world case, that's why this is not preferred in computers. And that's how a Gaussian elimination is a much better technique to approximate B from this.
Yeah, so I understand what they're trying to say. What they're trying to say is analytically trying to
Right.
do it is not advisable, but approximate solutions of A inverse will be better off, right? Because now whatever we use is approximations itself.
Correct.
Correct. Okay, I get it. Thank you.
Like, do you have like any idea? I think I just saw on internet. Gaussian elimination takes roughly O of n cube time to calculate the inverse, and traditional methods take O of n to the power 4, where we have n cross n matrix.
Okay. There'll be, I mean, obviously gradient descent is, an approximate way of doing the same thing. Also could be matrix factorization, right?
Okay, yeah, matrix factorization would also help. Yes.
Right. I'm not sure what the order of is for those.
Yeah, I think what Sujit said, I think in real world, it would be very difficult to find the right X which can give us B, right? So it's always an approximation. And the way that we generally do is we have to break down this A in such a way that computation becomes very easy. And that's how this diagonalization or SVD later on can help. And in those cases, most of the things will eliminated. And we will find an approximate b, because most of the time this b we won't be able to calculate because it will not be in the same space. Maybe later on I can explain with one of the example which I've seen. I took some notes as well which I can share later on, but most of the time we will not find a linear combination where b is in the column space of A.
Okay. Interesting. Okay, let's go ahead. Linear dependence and span. So, as I think we were discussing earlier, if there are vectors or columns which are dependent on each other, we can convey the same information, then they won't provide a linear independent combination. So we can, if we are able to represent even a single vector in terms of other vectors in a linear combination format, then they are dependent vectors. Now the span is like how much area we can cover. So if we have set of vectors, how much points in the space they can cover is their span. Through linear combination, okay. Through linear combination. Okay. Mm-hmm. So linear dependence. Now, if the determinant is 0, we know it is singular matrix, and it means that some of the one of the column or one of the vector is probably dependent on the other columns. Then come into norms. So this is the LP norm. And it satisfies these properties. If f of x is 0, then x is 0, triangle inequality, and so it forms a metric, I guess. So we can represent it as a distance from origin in some format. So generally we use the L2 norm, which is the Euclidean norm in deep learning, or the L1 norm sometimes. So I think they have discussed that. So the L2 norm may be undesirable in some cases because it increases very slowly near the origin. the squared L2 norm.
Yeah, the same, I think.
Yeah, so we use L1 norm when we want to preserve and we want to find something close to the origin. So L1 norm is commonly used when difference between zero and non-zero elements is very important. L0 norm is incorrect technology. Okay.
Yeah, it feels like the Hamming distance, right?
L0 norm is having distance.
Well, I mean, you could use the L0 on each vector, and then you calculate
Okay.
the difference. That is the Hamming distance.
Okay. Okay. Interesting. Number of non-zero elements. Okay, then we have the max norm. Again, that is L infinity norm. I think we have to take the limit to obtain that. Then Frobenius norm.
No, there's no limit here, right? You just take the max value in the vector.
No, I think here also if you put P infinity, the maximum value will matter the most. So like we can just take probably e to the power summation of mod xi to the power p, and if we take limit p tending to infinity, then we can reduce this. We can take the maximum outside x max 1 plus 1, I mean other mods upon x max and so on, the power p, and this will then tend to 1.
Oh, okay.
This all will be 0.
Yeah.
Cool. Makes sense.
I only got confused. Okay, here it should be log. That only I got. Here it should be log.
Right. Yeah.
Yeah, understood.
No, yeah. Then we will put like if you apply L orbital, you'll get direct L orbitals in calculus. But I mean, I think you can get this by putting P as infinity. I mean, limiting to infinity. Then we have a norm of a matrix, which is not a single dimensional vector. And Frobenius norm is defined as the sum of squares of all elements and then just taking root of special kind of matrices, diagonal matrices.
Can I ask a question? Oh.
Sorry?
Yeah, can I ask Frobenius norm, because they use it later?
Sorry, I cannot hear you properly, actually.
Is it better?
Yeah.
You see the I and J? Do you think it's the the sum of each. Yeah, I'm not sure. Sorry, there are two components, but there's only one sum. That's my confusion.
The two components.
Yeah.
I and j. There's only one sum sign, but there is.
Oh, I see. Okay. Square matrix, maybe that's why it's summation over I and j. All elements
So
of I and j. Yeah. All
if
elements
we
of A.
have
Yeah.
if we have matrix like this, you can just add the squares of the elements. That is 36, 25, 16, and 4. That is how much? 56 and 81, I guess. And
Okay.
then we take the root of 81,
Okay.
Nice.
which is 9.
So what's
So
the difference
basically,
with the? What's the difference with the L2 squared?
I don't think there is. It's the same.
Okay. Yeah.
I mean, L2 norm is defined for a vector, and this is defined for a matrix. That is like,
Yeah.
so
Okay.
norms are defined for vectors in general, because vectors can be represented as a point location in space, and the norm represents the distance from origin. So for matrix, we have just taken the intuition of L2 norm and defined it like this, I guess.
Yeah. Okay. All right. Thank you. That was insight for me. Yeah.
Do we
Okay.
know
Then
Frobenius norm anywhere? Like what is the application?
I think I've seen, but I forgot. Does anyone remember?
No, they use it at the end for the PCA.
PCA.
Okay, SVD. Got it. Okay. So diagonal matrix, I think everyone is familiar with the diagonal matrix, where there are elements in the diagonal and rest all are 0. Similarly, you have upper triangular, lower triangular matrices, where one part is filled, other is 0. Then symmetric matrices where transpose is equal to A, that is symmetrical. So it would be necessary for A to be square in shape. Then unit norm, unit vector, I think everyone knows. You can just go ahead.
Here I have a question. They say that at most n vectors must be mutually orthogonal.
Yeah.
I think below the unit vector definition, the paragraph below that.
Yeah.
Third line in that paragraph.
Okay. So let me just read it. Vector x and y orthogonal if x transpose y is 0. So it's like dot product is 0, 90 degree, right?
Right.
So in r to the power n, Rn, at most n vectors may be mutually orthogonal with non-zero norm. Because since it is r to the power n, I mean, since it is n-dimensional space, if there were n plus 1, for example, let us say a number greater than n, let us take the least number, n plus 1, mutually orthogonal vectors, then they so they will create a point. I mean, okay. Let me just think.
Yeah,
Another
this statement I did not get it.
another way to think about it, if you think about the output is identity vector matrix, right? Which is basically a diagonal matrix with ones down the diagonal, right? So unless your vectors are orthonormal, so everywhere else it is going to be 0, right? We know that because they're at right angles, but except with itself. So that diagonal has to be ones. If it's not unit, then it will not be one. It will be something other than one, right? So which will not turn into an identity a matrix.
I think
This is
I think
before they define
she's
ortho.
asking that why can't there be n+1 orthogonal, mutually orthogonal vectors in n-dimensional space?
No.
So,
I just did not
right?
not understand the sentence itself. Why do they say at most n vectors must be mutually orthogonal?
Because for example, we have 3D space, right? What they want to say is like even in 2D space, we only have for one vector. If we choose like this, we can only have
one which is right angles. Yeah.
We cannot have any other, because the other would for that we would have to bring another dimension.
Right.
That is the third dimension. So to prove this mathematically, we can prove by contradiction, I guess. But let me brainstorm and come back to you later, I guess.
Yeah, the part where I did not get is what do they mean by at most? So what is the minimum threshold for it is my question. Like how many can be mutually orthogonal?
Minimum is like up to you, right? Like if you take one vector and if you do not take any other vector, then you have a system where only one vector is probably, or so
no, 0 or 1,
they're
right? In 2 dimensions.
Yeah. So it depends on your system of vectors. Whatever vectors you choose in your system. So here, let us say there are 2 mutually orthogonal vectors, but this can be even in like 3 dimension. And we can take two orthogonal vectors in 3 dimension, right? We can also take three orthogonal vectors in 3 dimension, but we cannot take 4 orthogonal vectors in 3 dimension.
Yeah, that's where I was confused. When you're already telling it's in Rn space, why would you say at most n vectors? You can directly, I mean, it's understood, right, that beyond n you can't take any other vectors into consideration because the space is only Rn. That's where I was confused with the wording.
Yeah.
It's understood. Yes.
Okay, great. I was just confirming my intuition. That's it. Thank you.
Yeah, it's understood that if it is n-dimensional space, only at most n can be perpendicular.
Right. Great, we can move on.
Now, if the magnitude is 1, then they are orthonormal. So regarding the matrices, I think we have defined orthonormal only, and there is nothing not orthogonal but fully orthogonal. Only we have defined 2 matrices orthogonal when their product with its transposes identity. That is this. Okay. So let's do one thing. So as we have already completed like 2 hours, do you want to take the further session in the next session? I mean, further parts of this chapter,
Yeah, makes sense.
Yeah.
right? And we can focus on, I mean, like these were the basics till now, I guess. You can focus on eigen decomposition, SVD. You can do some problems on this topics if you want to dive into theory, or you can suggest anything if you have in mind.
Yeah, we can actually spend more time on this in the next session because there will be questions trying to understand the equations and everything, right? Especially for the PCA and yeah.
I think linear algebra will form our foundation of interpreting all the equations ahead.
Correct.
So I think we can spend time on, probably we can spend time. Uh, does anyone else have anything to say about this?
No,
Yeah.
sorry, I support you guys. The decision. Yeah, sorry, Suman, please go ahead.
I just echo that. So I think there are a lot of things that have been mentioned in this chapter very briefly, like span, linear combination. But I think we may like to spend some more time on solving problems. So I have actually put a few of the problems which I found from here and there. I put that in a note so that I can share. Uh, I will keep on adding problems. I completed the chapter read, but I have not completed the problem solving. So maybe we can discuss this problem next in the next week. And I personally felt that a lot of things I understood, but when I got a problem, I realized that I did not understand that properly. So problem solving, especially on this particular subject, is very, very helpful. So we may like to spend some time on solving problems.
So can we do this? Maybe the next session also, can we focus on linear algebra itself, try to finish the chapter and understand doing problems, and then maybe the next to next session we can do probability based on how it goes, right?
Yeah, definitely. I think we can do that. And actually,
Instead of rushing through it.
I saw your you mentioned the book of Gilbert Strang in the introduction, Suman. So I went through that book. It's really good. It's really good for linear algebra.
Yeah, he has a course as well.
Yeah, there are lectures and they're very intuitive. He explains it very intuitive.
Yeah, so I think one thing is like what the question that I think Ratna, you asked that why we cannot have more than two linearly independent vector, which is orthonormal or sorry orthogonal in R2. I think these are the questions which are very simple, but it's very difficult to explain if you don't understand it to its core. So one of the explanation that I've found that if you have any n-dimensional space, you can consider n as 3, let's say. We can maximum find 3 vectors which are orthogonal, perpendicular to each other. The fourth vector you cannot discover. We cannot find it in that space. The only thing that you can find is 0. So 0 is always, you can draw a line and have 0 and passing through that 0. And we can always say that 0 is orthonormal to that line, but that doesn't say anything about, that vector. So at max, we can get that n perpendicular vectors in that n space. Basically, n linearly independent vectors in that space. So I think we can spend some time on this linear algebra, because what I learned is if I understand these linear combination, thing, I think later on when I look at transformer, right, it's very, very easy. Like you just get it in the first go, what is happening there. But to understand the space and all that, it took me some time to, at least I don't know anything about it, but more time we spend on this, it would be beneficial to understand the later concepts.
Right, and this book, it's
Actually,
just covering the formulae and the equations, just trying to be a reference, but if we want to actually understand it, I think the Gilbert Strang lectures are really good. I've gone through that before, but it's been a very long time.
Actually, regarding the n+1 dimensions, I remember solving this. I mean, I think we can prove that the n+1 vector is a linear combination of the other n vectors, but I don't remember how to do that right now. But let's it's a good question. Let's brainstorm it and let's discuss in next class also.
Sure. Yeah. And I shared one link. Maybe I'll put that in the Slack. This is the note that it's basically you can find a lot of questions. So I'll just paste it there. It's very rough, but you can find few questions, and and if you have anything, you can just add. But I'll keep it updated for everyone's read, and maybe every week we can go over those questions.
Yes, Suman, your notes looks good. You've done a lot of work.
Sure. So let's wind up and let's focus on again linear algebra in the next session also. Okay. Thank you guys for the session, attending the session. Bye everyone.
Cool. All right. Bye.
Thank you.
Bye.
Thank you. Yeah.